I'll be here Wednesday, which is good. Oh, so Tuesdays are lab here. Yep, no lab Tuesday. But like I told you, I bumped the test. So the test was scheduled for the 2nd of April, and now it's going to be the 9th of April. So notice that I had listed on the 2nd, April 2nd, we would do a Lewis structure lab. And now I'm kind of thinking of pulling that into lecture, so I not know what we'll do. So you're, any questions about that?
So, no class Monday, Tuesday?
No class Monday and no lab Tuesday.
Okay.
Yeah, I'll be out of town.
So,
So you'll only be here Wednesday, which should work fine. Because, yeah, so you still have the following week. Yeah.
So Friday afternoon, you go over part 6.
So, you mean the day that you're going to be gone?
Yeah.
I'm not sure. So yeah, so no class here, and you'll be here Wednesday, but you won't hear be the 29th, and there is not a test here. So, but you'll be here Monday and all that. When I look at, let's see, what did that? Let's see if I can pull this up. Oh, this would be faster. I think it'd be faster. Because your question was kind of, I looked at it, I think we're doing really good for time, especially if I bump that later. Where are you guys? Here. So, as a teacher, I like to look at this column because this is how many slides we need to cover. So today we should be pretty good in covering part 4. Yep. And then part 5 would be Wednesday. And so what might happen is the Friday that you're gone, I might do that kind of lab activity we were going to do over Lewis structures. And then if you have questions, you can ask Gabe or me. So there's a good chance that Friday I'll kind of use that. And then when we come back Monday, then we would pick, in that scenario, we would pick up with part 6. So probably would not cover part 6. I don't know. But then you're a good student for wanting to know. So, but that's kind of what I'm thinking right now. Would be good use of our time. So, kind of building up to Lewis structures, we need to talk more about covalent bonds. Okay, so because like when I put up the compare molecular compounds to ionic compounds, for molecular or covalent compounds, all of the bonds, all the things connecting the atoms need to be covalent. And covalent bonds means electrons are being shared. So I actually have some kind of review slides here. Where is everybody going? So covalent bond is a sharing of sharing of electrons. Could be 2, 4, 6 actually. And a molecular compound contains only covalent bonds. Okay. And again, this feels like review. It's like, I said this already, and you're right. So ionic compounds, I said look for the metal. Okay. So ionic compounds take a metal and a non-metal, cation and anion. If you cannot find a metal in the formula of your compound is most likely a covalent compound, a molecular compound. Remember, covalent compound and molecular compound are synonyms for the same thing. It's the opposite of an ionic compound. So electrons must be shared to connect those atoms together. We talked about that X-looking thing is the Greek letter chi. That X means electronegativity. And I kind of describe it as a tug of war between two atoms that are stuck together, trying to stick together. If we look at the electronegativity difference between two nonmetals, It's not going to be high enough for the one with the high chi value, high electronegativity value, to have abscond onto electron, have an electron transfer. Okay? And we actually, and this will come up into play when we're drawing Lewis structures, electronegativity, what we say increases across the group, increases across the period from left to right. And with regard to the group, electronegativity increases from the bottom up. And you kind of see these electronegativity values of some select nonmetals. Okay. So, when chemical bonding occurs, whether it's an ionic compound or molecular compound, electrons transferred, electrons are shared, they're doing so to get the rare gas configuration, sometimes called a complete octet. But I will warn you that the rare gases are group 8A elements. These have an octet, their valence shell 88888. But this guy is also a rare gas, valence shell 2. Okay, so we're going to see hydrogen likes to pick up or share an electron and become like helium. So on the structures that I'm going to show you, and this will make more sense when I show you. Well, I'll just kind of show it to you abstractly. If we have atom A, and it's going to be chemically bonded to atom B, so I'm going to show a solid dash for a covalent bond. As it turns out that every time, and this will make more sense in a minute, anytime you see a dash, that's going to actually be 2 electrons. And those 2 electrons, it's kind of like Venn diagrams. Those 2 electrons, it's joint custody, are jointly, the atom A can say it has it, and the atom B can say it has it. And so that's what we mean by double dipping. So the electrons are shared. And so those 2 electrons can contribute to a complete octet for A. Those 2 electrons can contribute to a complete octet for B. Now, as I've drawn it, I don't have the other 6 electrons. Okay, but that's kind of how that works. Okay, so it's all about octet, 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 except if it's boron. And boron doesn't want 8, boron wants 6. And this other one we don't really talk about, I don't spend much time in introduction to general chemistry. I go a little further in general chemistry. But elements that are period 3 or greater, you're like, dang, period 3 or greater, that's like the whole periodic table. I think I could have said elements that are not in group 1 or group 2. So period, that are not in period 1 or period 2. Period 3 or lower actually can have what we call an expanded valence. And specifically, they'll have more than 8. They'll either have 10 or even 12. More than 8. You're going to see when the dust finally settles and they connect to other atoms, you're going to see actually 10 or 12 electrons associated with them. I left room down here because I think on the slide I'm going to add, I mentioned hydrogen likes to become like helium, so I'm just going to say something to the effect that hydrogen, the element hydrogen, I'm going to say wants to possess or to share 2 electrons. Okay? And in doing so with 2 electrons, it's, like I said, it's going to be like the rare gas helium. Cool. Okay, so we, in this class, talked about the scientific method of discovery, and I'm sure you've been exposed to it before, but we start out with observations, and from those observations we create hypotheses, like your science project and all that. And then hypothesis can be ruggedly tested. We do experimentation to reinforce, or we have to adjust our hypothesis, and we can elevate a hypothesis up to a theory. I just mentioned that because sometimes you say, oh, it's just a theory. It's like, no, it's a theory. That's an awesome thing. Okay? So there is this valence bond theory, and it's a simple look at it using quantum mechanics, or it uses quantum mechanics. We're going to look at it very, very, very simply. So covalent bond theory. First off, And I think this is pretty cool. So I have atom, let's see, how's that work? Yeah, I have atom A and atom B. And we've been talking about, I'll start with atom A. We've been talking about different electron orbitals or atomic orbitals. That's your, S, P, D, and F and different principal energy levels. I'm going to pick on the S, and I'm going to pick on the P. I think the P's are cool because actually we said that those are double low. So this could be an atomic orbital that's a P, okay? And then I'm going to go over here, and it works with S too. I like P's. So I'm going to draw my atom B, and I'm going to go ahead, and this is an atomic orbital of B. It's actually a P-type atomic orbital. So what happens to connect A and B is actually where the connection is going to occur is created, like this slide says, a bond orbital from the overlap of two atomic orbitals. So here's atomic orbital, and this is my new bond orbital where the overlap is. I just think that is so cool. So that's actually going to form into that. And I could put, and this represents the nuclei of the atoms and the other electrons, but I could draw them closer, and I got a greater overlap, and actually that would be a stronger bond. So it's pretty darn cool stuff. So this is my bond orbital. So my bond orbital that's created by the overlap of two atomic orbitals, actually, kind of like an atomic orbital, I need to have two electrons there. So I need to have two electrons, and actually I've kind of come full circle. I said that I'm going to have two electrons with that dash, two electrons right there. It's the same thing. Oh, so it has two electrons in it, and they have to have opposite spins. We've talked about that before. So all that means is I have one up and one down. So it's kind of nice when thinking like, yeah, I've heard of spin before. Now this says that those two electrons, you don't have to have one electron from atom A, one electron from atom B. They could both be from one atom, or both be from a different atom. Okay, so it kind of has some possibilities there. So I'm going to draw some structures on this slide to kind of show you what I mean by single, double, and triple bond. So I'm going to start with C2H6. Okay, it looks like this. These are what we call Lewis structures. So I'm going to put a carbon bonded to a carbon, and then I'm going to put 3 hydrogens on each carbon. And those dashes are kind of like the dash I put up on the board. Those dashes represent the covalent bond between the atoms. Okay? Those just all happen to be single bonds. So we know we have 2 electrons being shared between all of those atoms. A double bond, an example of something that has a double bond would be my C2H4. And to draw that, I'm going to put carbon, double bond, carbon, and then each carbon has 2 hydrogens. So notice that I put 2 dashes between the 2 carbons, and that's an example of a double bond. So that double bond is 2 pairs or 4 electrons. So I'm going to put 4 electrons there. And these are Lewis structures. All right, the last one, we need to show a triple bond. A good one for that would be to keep with the same pattern, C2H2. And so I have carbon, 3 dashes, triple bond, carbon, and then each of the carbons have a single bond hydrogen. Okay, and so like this slide says, that those 3 lines represent 3 pairs of electrons being shared. 3 times 2 is 6. So I have 6 electrons there. So that's actually going to kind of get you down the road or be helpful when you're drawing your Lewis structures. All right. So there are 2 types of covalent bonds. There are 2 types of bonds in which electrons are shared. I call this one the first one to arrive. It's called the primary bond, and it's called that we use the Greek letter sigma, so sigma bond. It's the first to arrive. What else? if you have two atoms like atom A and atom B are going to be stuck together with a covalent bond, then it has to have a sigma bond. So guess what? This is a sigma bond, as I've drawn it. Okay? Bada boom. Note. So all single bonds are sigma bonds. Sigma bond. So we have a pair of electrons that are hanging out in a bond orbital. That was formed by the overlap of two atomic orbitals. Pretty cool. So I brought these to kind of help with this. So a minute ago I did the C2H6. This is C2H6. So we have our two carbons that are singly bonded, and then we have each carbon has three hydrogens singly bonded to it. So those grays represent actually sigma bonds. And like the slide says, sigma bonds, first derived primary bond, all single bonds are sigma bonds. And so actually those two electrons that are joining the atoms lie along a line between the two nuclei. C2H6. All right. So I had a grandmother, it's been past deceased for several years now, but she was all about dessert. So we would go to Country Kitchen for Madison, and we would, she'd get dessert first. So if you're not a grandmother, you're supposed to eat your main course first, and then you can have your dessert, get it pie as dessert. So we actually have this secondary bond that if you have a sigma bond, then you can have a pi bond. So the way this works is, again, after you have your sigma, then you can have pi. Not the way my grandmother did it. So a little bit ago when I drew the second structure, I had carbon double bond carbon. Oops, sorry. Carbon double bond carbon. The first to arrive was the sigma, and the second to arrive was the pi bond. Goodness, my pen is just not a happy pen. Okay. The third structure, I had the two carbons were triply bonded. Carbon, triple bond carbon. Again, the first to arrive is the sigma, and we actually end up with two pi bonds. And it all works because each bond, whether it's sigma or pi, is a pair of electrons, so you end up with 2, 4, 6. You have 6 electrons sticking those two carbon atoms together. You think there's a lot of energy with that triple bond, you're right. So the last thing we need to talk about is where do those pair of electrons that are creating that pi bond, that are attaching those two atoms together, where does it go? Because it can't go in the middle. And here's the answer to that. So this is my C2H4. So of course we have the sigma bonds to the hydrogens, those are the gray blobs. And we have the sigma bond between the carbons. And then for the pi bond, actually that represents one pair of pink and purple. So like the slide says, or like that last note up there says, those two electrons that create the pi bond actually they hang out above and below the sigma bond, outside the sigma bond. So that's a double bond, and this is a triple bond. Carbon, single bond hydrogen, single bond hydrogen, and here's my sigma bond between my two carbons, and so I need a pair of pink and purple to represent pi and pi. So it's a busy sort of deal. One of the things we'll be talking about is a little bit of shape or geometry around an atom. And maybe you can see we definitely have different geometry around this one, carbon triple bond carbon, versus this one where we have a carbon single bond carbon. I'll talk about that geometry coming up. Okay. So there are some subjects when I get to a science I'm like, don't blame me, or I say, I know it's confusing, but welcome to science. I wish they would have come up with a different name for this. Sometimes I would call this the expected valence of an atom. The reason I don't like it is because we talked about valence electrons, and valence of an atom is not the same thing as valence electrons. What did I do? There it is. So I sometimes call this the expected valence of an atom. And sometimes I will call it the number of times that an atom will reach out. Number of times atom reaches out. And when I say reaches out, actually, you can kind of see on the slide, that's the number of primary and secondary sigma and pi bonds that an atom will form. So for the main group, for the group A elements, I shouldn't say main group. For the nonmetals, what is this, 4A through 8A, we can calculate the valence by expected valence by taking 8 minus the group number. Expected valence, again, the number of times you expect an atom to reach out. And actually, I'm going to take it up a notch. It's not just any atom. It's an atom that is in a neutral molecule. So there's some catches to all of this. So applying that rule, 8 minus the group number, we have some exceptions. Hydrogen only wants to reach out once. That's it. Once. One time. Connect with one thing. And boron, because it doesn't want a complete octet, it wants a complete set of 6 electrons, it wants to reach out 3 times. So the expected valence of hydrogen is 1, expected valence of boron is 3. Now, this slide applies you see the expected valence, number of times. Remember, this would be the sigma and pi bonds. Okay, and again, how did we get that? We took 8 minus the group number. So, for instance, carbon is group number 4. Carbon's 4A. So I take 8 minus 4, we expect it to reach out 4 times. Going over a group to nitrogen phosphorus, group 5A, 8 minus 5. 8 minus 5 is 3. Sulfur and oxygen, 6A, 8 minus 6 is 2. Halogen, 7A, 8 minus 7 is 1. So again, that's the number of times you expect them to reach out. I said hydrogen's going to reach out 1 time, boron's going to reach out 3 times. But this only works, it has a little bit of limitation if it's a neutral molecule, an atom in a neutral molecule. Here again, I think we looked at these before. These are Lewis electron dot formulas. Remember, the way this works is the symbol represents the nucleus or the center of an atom and all electrons that are non-valence electrons. So, if we just pick on, for instance, fluorine is a 7A, so it should have 7 valence electrons. You see 7 dots here. And so actually, underneath the bottom here, I'm going to put valence, expected valence. We said expected valence of a 4A carbon is 8 minus 4 is 4. The 5A nitrogen, 8 minus 5 is 3. 6A oxygen, 8 minus 6 is 2. 7A fluorine, 8 minus 7 is 1. So I kind of almost pretend like sometimes it's, oh, by the way, the rare gases, group 8A, 8 minus 8 is 0. So you expect it to reach out 0 times, that's why they call it inert gases. But I kind of pretend like these are like little garages, and you can see where I have 1 place here to park a car. I have 2 places here to park a car. I have 3 places here to park a car, etc. 4 places here to park a car. If my goal is to get a complete octet, and as I park my car, I'm shimmying up an electron to be shared. So that works. All right. So Lewis structures, again, like I said, RJ, the next lab listed that we would get to would be the Lewis structure lab, and I'm thinking I'm going to reel that into lecture, I think. But when we make these Lewis structures, which a little bit ago I made the Lewis structures of the C2H6 and the C2H4 CH4 and the C2H2, those are Lewis structures. They give us a sense for how the atoms are arranged, okay? The first step, and I think we're going to look at it just a little bit this morning, the first step in drawing a Lewis structure is to come up with a pot of valence electrons. And I just like that term, pot, like a cauldron, so pot of valence electrons. The pot of valence electrons will be distributed or kind of strewn around your Lewis structure, and those pot of valence electrons can either be a dash, which means that they are a pair of electrons, either in a single, double, or triple bond, or they can be what I call a dot dot. This is my dot dot, a pair of lone pair electrons. They are part of the pot, and they are only associated, though, with one atom. They are not a pair of bonding electrons being shared between two atoms. And this is one of the subjects where it's almost easier to show you than to describe it to you. So Lewis structures, kind of like we've been talking with the electron dot structures, we're going to have the symbol. Think of the symbol as representing the center of the atom, the nuclei, and all the non-valence electrons. And we'll do 1 dash for a single bond, okay, 2 dashes for a double, 3 dashes for a triple, and again, the dot dot. On Lewis structures, oftentimes you'll kind of see this north-south, east-west sort of thing going on, top-bottom, left-right, but there's no significance, like you kind of saw me parking cars next to those electron dot formulas of the period 1 nonmetals. Lewis structures, in and of themselves, they don't depict 3 dimensions because they're flat, they're paper and pencil. But I'm going to try to convince you of this when we talk more about Lewis structures, that you can kind of make it come alive in your own mind, or draw or come up with a model that will give it 3 dimensions. Okay. So I'm going to show you the Lewis structure, or you already see the Lewis structure of ammonia, but what I want to do, oh, go ahead, right here. What I want to do is go ahead and show you that pot of valence electrons that you would, how you would start to draw your Lewis structure. So it looks like this. For nitrogen, the element nitrogen, I have 1 nitrogen atom. Now, with regard to the number of valence electrons, I just have to look at the group number. So nitrogen, group number 5A. So I'm going to take 1 times 5 electrons. Yeah, I get collectively that nitrogen atom's got 5 electrons going on. Hydrogen, the element hydrogen, I have 3 hydrogen atoms. And this is where you would find hydrogen over, well, I guess it is over here. So hydrogen has 1 valence electron. That's totally true. So collectively, you're looking at 3 valence electrons. Oops. I'm not going to draw a line yet. There's 1 more. Yeah, no, that's it. So if I take 5 plus 3, you're looking at a pot of 8 valence electrons to be strewn around my NH3 molecule. So I just want to kind of confirm that when this final Lewis structure, somebody drew it with a single bond between the nitrogens and the 3 hydrogens, and also over the nitrogen a dot dot, a pair of lone pair electrons. I'd like to confirm that that pot of electrons shown in the final Lewis structure is equal to the pot of valence electrons I know should be brought because of the formula. So if we know each dash in a single, double, or triple bond is 2 electrons, I'm liking 2, 4, 6, and 8. So I have 8 electrons on the final structure, and that actually then, at this point, I just want to kind of confirm that that's equal to 8 electrons that I anticipated. The other thing I want to kind of point out is that if I were to, they kind of remind me of Venn diagrams, sort of. If I were to draw a circle around the hydrogen, I would see that the hydrogen has joint custody with that nitrogen of 2 electrons. So this guy has 2 electrons, which actually what I said is hydrogen only wants 2 electrons. It wants to be like helium. So those other 2 hydrogens are the same thing. Let's draw a circle around the nitrogen now, and we have to encompass all the electrons that are shared with the hydrogens, and we have to encompass its lone pair electrons. Now, we've been talking a lot about octets and all that. 8. Can you see where, with regard to the circle that the nitrogen is in, I have 2 electrons shared with that hydrogen, 2 electrons shared with that hydrogen. They get the joint custody of 2, 2, 2. That's up to 6. And also, nitrogen has a pair of lone pair electrons. So when I talk about complete octets, that's what it has. So that guy has 8 electrons around it, and i.e. complete octet. All right, so let's take a look similarly at formaldehyde. Let's come up with a pot of valence electrons. Hydrogen, there are 2 hydrogen atoms. They both have 1 valence electron, so I have 2 valence electrons there. With regard to carbon, I only have 1 carbon atom. Carbon is, again, we get the valence electrons from its group number. Carbon's 4A, so it has 4 valence electrons. And then oxygen, there's only 1 oxygen atom, and oxygen is 6A, so I'm going to put 6 there. So you're looking at 12. So let's just double check on this final Lewis structure. Do we have 12 electrons shown? So I'm looking 2, 4, 6, 8, 10, 12. So yep, this is showing 12 electrons on final structure. And let's just double check the whole octet thing. I'm going to ignore the hydrogens because they have 1 bond where they have a pair of electrons that makes them like the rare gas helium. That's awesome. So that's 2 electrons for the hydrogen. Well, let's draw a circle around the carbon. And doing so, I'm looking at 2, 4, 6, 8. So, yep, that carbon atom has a complete octet. And then if I draw a circle around the oxygen, it's got 2, 4, so it's got 4 electrons shared in that double bond with the carbon. 4, 6, 8. So, yeah, it's got a complete octet. So that's all a happy Lewis structure. Let's look at one more structure. So again, let's take but this is different because it's not a neutral molecule, it's actually a polyatomic ion. So let's look at chlorine. There's 1 chlorine atom. If I find it on the periodic table, it's 7A, so you're looking at 7 valence electrons. Oxygen, I have 1 oxygen atom. It's 6A, so you're looking at 6 valence electrons. And you have to kick in for the charge. So actually, it's a -1 charge, so I just put charge here. Charge is a -1, so I'm going to have to add 1 electron. If it had been positively charged, I would have had to take in 1 electron away. So I got 13 normal electrons and 1 electron from it being charged, so I'm looking at 14 electrons. So let's look at this final Lewis structure, see if we have 14 electrons. So I have 2, 4, does my quiz show up? I've got 2, 4, 6, 8, 10, 12, 14. So yep, I've got 14 electrons here shown. And now you don't know yet how to make this Lewis structure, but I'm going to talk you through some clear steps on how to get that. So 14 electrons shown on final structure. That's great. And let's check for octets. So I could draw a circle around this chlorine atom. So I just think that's kind of cute where actually it has sole custody of 6 electrons because it's got these 3 pairs of lone pair electrons. It's got sole custody of those, and it has joint custody of these 2 electrons. So 6 plus 2, it's got 8. So that's how it has what we have complete octet. Let's draw a circle around the oxygen atom. And again, it's kind of sort of a symmetrical polyatomic ion. So 2, 4, 6 that it's got a sole custody of and joint custody of 2. So yep, you're looking at a set of 8 or an octet around the oxygen atom too. So I don't know how you want to adjust or amend this slide in your notes for this part 4. But let's see, assignment, hold this thought. Okay, these problems will be assigned, but notice that they are only due after we cover drawing those structures. Does this say all that stuff in anything?
Yeah.
The one thing, if you want to amend it, you might want to draw a line through it in the laboratory exercise, because I'm not sure if it's going to be a lab or in class. One of the things I didn't mention, but the fact that we're bumping the test due to kind of my conflicts means that we might begin, like I threatened or we might begin new material for a new unit even before you take this unit exam. Just because. So that's all I got.
I didn't have scissors at home, so I gotta go cut my flashcards out of the library.
You can even bring them next week, that's fine.
Okay.
Yeah, there's no time limit on that one.
Alright.
Yeah.
Yeah, because I was looking around, I was like, oh, I have scissors.
Oh, and the other thing I'm trying to get the word out, for all of your classes, including this one, you will, on beginning Monday, be bugged to take an evaluation.
Survey things?
Survey thing, yeah, for all of your classes. And most teachers, myself included, like you to fill those out, because actually, if you do comments, that's great, and it gives us an idea of where we can improve. Yeah, well, we're doing good, so yep, and if you don't take the survey, it will keep bugging you to take it, so just get over it.
So the one where I kind of can't take it?
No, it's a different one.
Okay.
Yeah, that one, the one we wanted you to take Wednesday was for the whole college, and this one's just for this class.
Okay.
So yeah. Very good. Have a great long weekend, people.
Are the Mondays after the 25th just normal?
Yes.
Okay.
It's normal speaking. And I told my other class that just recently, yesterday, I've agreed to be on 2 search committees for jobs that I think are really important or whatever. Obviously, I wouldn't be on them